People can hear differences in timing of only a few milliseconds. And when you have a good ensemble playing together, they're really tightly synchronized, especially like a jazz group, for instance. To have them be exactly synchronized to within milliseconds of one another is very important. Timing accuracy is important really to any instruments, not just to digital instruments. And I think it's because time is a fundamental part of musical performance. If you're performing on an instrument, you need to be able to know exactly when the events that you're creating are going to sound. To build a digital instrument, it's incredibly important that the timing of the instrument is really predictable, and ideally also that it's as fast as possible with as low latency as possible, so that there's a very small delay between action and sound. Designing instruments for low latency is certainly a challenge. There's a lot of ways that computer systems have been designed to process audio that don't have musical interaction in mind. Certain ways that audio is buffered, certain ways that it's processed in a modern computer that can result in a significant delay between action and sound. And even worse, it can result in a lot of uncertainty in the timing, potentially a variation in latency of 10 milliseconds or more. And this is something that the performer can't adjust for. If you don't know when the action that you're taking is going to sound, there's no way that you can place it precisely. And it's a really big problem.
Time synchronization is really about comparing your clock with a reference. So your reference could be a clock that you understand its behavior very well, like a cesium clock, or a GPS signal will give you a very accurate time signal. And you need to compare your clock with that other clock. So you want to compare the two frequencies of the two clocks, and also a 1 pulse per second generated from each clock can be compared. And that way you know the frequency difference between the two clocks and their time difference.
Networked musical performance is an area that's been people have been interested in for a couple decades, I would say, at this point. And there are a lot of challenges with that, especially if you're talking about people playing in remote cities that are quite some distance from one another, where even the speed of light actually becomes a significant latency. That if you're going from London to Los Angeles, there's simply no way that it won't take tens of milliseconds to be able to transmit network information from one to the other. And here you end up with a really fundamental question of what does it mean to play together when you are remote from one another, and exchanging information is going to take an amount of time that is significant for musical performance. So is one person's time the right time and the other person has to adjust to that, vice versa? It's really quite unclear what the answers are for this.
The global metronome is inspired by like physical ensembles, which is, in the case of the orchestra, there's already delay between players. Music takes about, I think, 1 millisecond to travel 1 foot, but you have the advantage of light, which travels faster than sound, so you can have somebody up in the front conducting everybody, and they basically see what's essentially like a perfectly synchronized tempo source. And so the global metronome aspires to be that central source. You have like this virtual metronome, and then you have the global metronome implementations that are all synchronizing to that virtual metronome. And so everybody who's wherever on the earth can see, but they'll know that they're synchronized with one another. The way that you make a global metronome is just two pieces. The first piece is that you need a way to synchronize clocks to a high degree. And the way that I do that right now is via GPS. Then once you have your clock synchronized, it actually becomes really simple to figure out when the next tick of the metronome is, as long as everybody agrees to compute it in the same way.
Each satellite in the GPS constellation has an atomic clock on board. Your phone, for example, has a GPS receiver and its own clock inside. And you need to have 4 satellites in view at any one time. You need 3 positional measurements and a time measurement. Your receiver will compare those time signals with your clock signal, and from that it can derive your position very accurately. And this is one of the reasons why accurate time is so important, because if you think the speed of light, it travels 30 centimeters in 1 nanosecond. So if you need a positional accuracy within a meter, you need to have 3 nanosecond time accuracy, otherwise you won't be able to get that precision.
Another approach, I suppose, is to network musical instruments directly. So if we're designing an ensemble of musical instruments, maybe we're not even talking about remote networked performance. Maybe we're even talking about people within the same room, each of whom has a digital musical instrument, and these instruments communicate with one another directly, as well as the performers communicating in their performance. And there you can start to talk about synchronizing the clocks of the instruments, making events happen at the same time on each of the instruments. I suppose technically it's a little bit of an easier challenge. It's not terribly difficult to agree amongst a group of instruments located together what the master musical time is, but the question is what do you do with that information, and how much time control therefore should be reserved for the musicians, and how much of it should be delegated to the machine. And so it's really as much of an aesthetic decision as it is a technical one at that point.
The aim of optical clock research at the moment is to reduce the uncertainties to the lowest possible level. As optical fibre, the stability of this time transfer method is very useful for the next generation of clocks, which will come in the future. So NPL is working on some optical-based atomic clocks. Fibre-based techniques will be used to compare these clocks at a distance, because the current standards are not good enough to compare the optical clocks. So how do you know how good your clock is if you can't compare it? So that's where the fibre comes in.
It is an ongoing challenge to design machines that can encompass the kinds of creative and expressive decisions that humans make. You'll see different authors describe this in different ways. It can be described as control intimacy. Sometimes it's described as transparency, the idea that the instrument sort of disappears from my consciousness so that I can think about the actions of creating music, because the operations that I need to manipulate the instrument become automatic. Intuition, of course, is a term that's used in relation to this. So this idea has been well known for decades, really, and it just is but it remains an open challenge of how to achieve it, I'd say. I think for designing digital musical instruments, we also need to consider which element of traditional performance we are seeking to extend or replace. Are we seeking to replace the role of the human performer, or are we seeking to replace the role of the mechanical system that used to be the musical instrument? And these are two really different design challenges. To replace the human cognition in musical performance is quite a difficult challenge and requires one set of design principles, whereas to make something that works really intuitively with a human performer is a different set of design principles. And I think one of the opportunities that is increasingly emerging is the potential for collaborative creativity systems where the human performer is very much still part of the performance. Their responsibility hasn't been reduced in any way, but that the machine also offers a kind of creative counterpoint. And so you find the machine acting simultaneously as instrument and co-performer.